Hi, everybody. Glad to see you again. And let's start our lecture number 9. Okay, so let's do it. Today, our lecture topic is optical sensors. The majority of optical displacement sensors are based on variable reflection or transmission. Optical force sensors are derived from displacement sensors by adding one or more spring elements. Since light is a wave, one can also make use of travel time, 2OF, phase, shift, and interference. And first, we discuss in this lecture the major optical variables and certainly parameters too. Next, we review the properties of some commonly used electro-optical and optoelectrical components as measurement tools. This subsequent section deals with methods on how to build up sensing systems for the measurement of position and displacement using such components. Special attention is given to the position-sensitive diode, PSD, position-sensitive diode, optical triangulation, and interferometry. This section also includes a discussion on optical encoders, like linear and angular, absolute, and incremental. The next sections deals with some basic electronic interface circuits. And finally, the last section is devoted to applications of optical sensing systems for linear and angular displacement, object shape and tracking, navigation, force, torque, and strain sensing. Most optical sensors applied in mechatronic systems are used for the measurement of displacement or distance between usually moving parts of the construction. Their output is used to control proper operation of the system. For instance, to perform a special action, like movement and rotation, or to maintain a specified condition, like position and force. A general setup of an optical sensing system is given in this slide. It consists of a light emitter on the left side of this slide, light source, and light receiver on the opposite side on the right side. Light detector. The light travels through a medium, usually air, but may include parts of the construction, from transmitter to receiver. The transmission path is influenced or modulated by the quantity that has to be measured. Various properties of the light can be affected by the measurement. This can be done in various ways, as shown in this table on this slide. The same table also gives various types of emitters, receivers, and possible accessories that may build up for the optical sensing system. Clearly, the large number of combinations give the designer much freedom in choosing the best solution for the intended application. And clearly, the application of an optical sensing system requires the incorporation of optical components in the mechatronic construction. They make up an integral part of it. And therefore, it is important to include the optical and any other sensing system from the very beginning in the design process of the mechatronic system. Since most optical sensing systems comprise a combination of a light emitter and light detector, we give a review of some of these optical devices and their properties. The next list gives commonly used emitters for the application in displacement and force transducers, together with a general characterization. For detailed information, you could refer to the data sheets and catalogs of the manufacturers, most of them freely available in the internet. The major types of the light emitters are thermal light bulb, a very cheap and easy to get optical source, also available in small dimensions. For instance, a bicycle tail light. Major characteristics of this wide optical spectrum, but almost white light, and wide beam angle, generally speaking, almost omnidirectional, and a slow and small bandwidth. Due to the thermal operation of the intensity cannot change very fast, and not suitable in modulated systems. LED, light emitting diode, a cheap and widely used light source for numerous applications, like illuminations, displays, and remote control. Main characteristics are next: materials, gallium arsenide, and others, maybe from 3 to 5 compounds, a relatively narrow emission spectrum. It looks like tens of nanometers, covering all colors in the visible spectrum and infrared. Electrically controllable intensity, so suitable in modulated systems, and moderately focused focused beam with built-in lens. Semiconductor laser or laser type. It is a low power type having appearance and dimensions similar to LEDs, but whose physical operation is different. Well known from CD and DVD players, laser pointers, and laser printers. And main characteristics are next: material, usually the same, are gallium arsenide, and other 3-5 compounds. Laser stimulation by injection of charged particles of color. Electrically controllable intensity, monochromatic, it means a very narrow spectrum, generally a few nanometers, and covering most colors in the visible spectrum, infrared and near UV ultraviolet, based on gallium nitride. Moderately focused beam, same as LED. Solid state laser, much more expensive device and suitable for large optical power. Its main major characteristic is the next: material. It's niobium and yttrium aluminum with neodymium ion impurity. Ruby, aluminum 2 oxidant 3, laser stimulation by optical means, usually like light pulses. Monochromatic, very narrow optical spectrum in visible spectrum and infrared. Narrow beam, intensity control only possible with special components. Gas laser, much more expensive device and suitable for large optical power. Major characteristics. Materials, first of all, it's helium neon or gas, and laser stimulation by gas discharge. Monochromatic, very narrow optical spectrum in visible spectrum, and certainly in infrared. Narrow beam, intensity control only possible with special components. Many other types of laser exist, mainly intended for other applications, such as cutting, drilling, and welding. For mechatronic applications, the LED and the laser type are recommendable devices because of their small size, simple interfacing, and easy to modulate. Important parameters to be considered when designing a sensor system are the output intensity of power versus input current or sensitivity, output intensity versus wavelength or spectral sensitivity, and output intensity versus angle of divergence or directivity diagram. There are a vast number of LEDs and laser diodes in the market. Some manufacturers offer the possibility to search in their database by particular specifications as are required by the design. For instance, by power range of wavelengths. For each product type, main specifications are tabulated, but not always in a structured, consistent way. Finding exactly what is needed for a particular application is still time-consuming. Graphical data provide better information compared to numerical data. In this figure from AD shows examples of such graphs. The output characteristics for a LED and laser diode, the optical spectrum, and the directivity. Intensity versus forward current you may see on the figure A on the left upper corner of this slide. And this figure shows that the intensity and power of a LED is about proportional of the forward current. The maximum intensity of a LED range from a millivolt up to several volts, depending on the type. The intensity drops with increasing temperature at a rate of about 1% per Kelvin. A laser diode in this figure B starts to laser from a specified forward current, typically between 50 and 100 milliamperes. And here, too, for intensity drops with increasing temperature, mainly because of the decreasing quantum efficiency at higher temperature. Wavelengths, a typical plot of the spectral emission is given on the figure C. You may see it on the left bottom part of this slide. The peak wavelength is determined by the semiconductor material type, as you can see on this table. In between values are also available. These colors are obtained by small additives of other materials. The optical bandwidth is the wavelength interval at 50 relative intensity. LEDs have optical bandwidth in order of 20 to 50 nanometers. A laser diode is much more monochromatic with optical bandwidth of only 1 nanometer. Directivity diagram you may see on the figure D, and this is on the right part on the bottom of the slide. Is an example of the directivity diagram. The half angle, denoted the beam width, is defined as the directivity in which the intensity has dropped by 50% relative to the intensity in the direction of the main axis. Main axis, it means 0 degrees. Here you see as a vertical plane. The diagram combines the directivity of two types, a narrow beam and a wide beam type. Narrow beam inside and wide beam inside. And usually, a small angle is obtained by a lens at the front. And you should notice that laser diodes have also a relatively wide beam angle. Due to the short optical path the light travels in the device, some types of laser diodes contain an additional photodiode within the housing, suited to monitor and possibility control the output intensity. Other important parameters to consider when choosing a light source are the temperature sensitivity of the peak wavelength. Usually it's about 0.1 nanometer per Kelvin for the LED. The rise and fall times when used a switching device, and the heat resistance when used near maximal power. Commonly used optical sensors and their general characteristics are photoresistor, small, cheap, sensitive to visible and infrared light, red light, no direction sensitivity, slow, large response time, and resistive sensor. Photodiode, small, cheap, sensitive to visible and infrared light, moderate directional sensitivity, fast response time, and also available as quadrant director, 4 diodes in one case. Phototransistor, similar to photodiode, somewhat slower. Diode array of photodiodes from a few in a single casing, up to over 4,000 elements on a chip. Line rate up to 100 kilograms. Gray tone and color. Position sensitive diode, PSD. Radiometric properties as photodiode. One-dimensional or two-dimensional position sensitive. CCD camera, area scan. Resolution up to 2048 for the same 2048 elements. Frame rate up to thousands over seconds for a low resolution type, grain tone and color. CMOS camera, area scan, higher resolution compared to CCD camera and somewhat worse noise performance. Line and area scan cameras are excellent devices to perform imaging tasks and hence play an important role in mechatronics and in particular robotics. The market offers a gradually increasing number of cameras with built-in image preprocessing. Pixel size of both line and scan cameras is in the order of 5 to 5 micrometers. Current research aims to increase the resolution, number of pixels, and the speed. Usually it's measured in either pixel acquisition time or frame rate. Chips with over 60 million pixels are visible. CMOS cameras have higher resolution because there are no charge buffers on the chip as with CCD. Moreover, camera and system clocks are synchronized, eliminating the need for a frame grabber and thus increasing the overall frame rate. Cameras will not be discussed further in this class. You could refer to textbooks on this subject and the information provided by the manufacturer. Okay? And now, on figures A and B, from all four figures, shows typical characteristics of photodiode. Voltage, current characteristics, sensitivity and temperature characteristics, and the special sensitivity. The direction sensitivity is given in a similar way as with emitters. Half angles range from 10 to 60 degrees, depending on the presence of a building light. Voltage current characteristics, as you can see on a figure A on the top left corner of this slide. This figure depicts four curves for different values of the incident light intensity. In the absence of light, the voltage current relation uppermost curve is the same as for a normal PN diode. An exponentially increasing current with forward voltage and a small leakage current, the dark current when reverse bias. When light falls on the PN junction, the leakage current increases because photons generate additional electron-hole pairs, which may result in an external current. As can be seen in figure A, the short circuit current, represented by the P bullet on the I-axis, increases in proportion to the incident light. The open voltage, represented by the circles of the B-axis, increases as well with the radius, but in a nonlinear way. Sensitivity characteristics. The photocurrent is proportional to the incident light over more than 6 decades. This you may see in a figure B on the right side on the top of this one. This is the main reason why the current mode or conductivity mode is preferred over the photovoltaic mode of operation. Current readout is easily accomplished using two operational amplifier in current to voltage converter arrangement. Usually a reverse voltage is applied to ensure the diode always operates in the flat part of the characteristics, as you can see on the figure A. That current not only light for optical energy, but also thermal energy gives rise to the generation of additional charge carriers around the PN junction. This is exactly why the reverse current of a PN diode is not zero. Roughly, the thermally induced leakage current doubles each 7 centigrade. At room temperature, the leakage current of a silicon diode is very small. Sometimes is nearly 10 picoampere. But since a photodiode has an essentially larger active area, its dark current is also much larger. And moreover, it increases exponentially with the temperature, as you can see it from the figure C. This figure you may see on the bottom part of the left part of this one. Spectral sensitivity, assuming a quantum efficiency of hundreds of cents, each incident photon creates one electron-hole pair if the photon energy is larger than the band gap energy E to generate a free electron. Okay? And you may see on the formula on the right of this slide, you may see here, the energy proportionals H times V to generate a free electron. And you may see on this form. Here, V is a frequency and H is a Planck's constant. So E of the material determines the maximum wavelength. Silicon has a band gap equal to 1.12 electron volts, corresponding to a limiting wavelength of about 1100 nanometers. The lower boundary of the spectrum is set by the absorption of the light before it has reached the PN junction, and in general, the absorption coefficient of the material involved grow with reduced wavelength. The result is a spectral band that strongly depends on the material, as you can see on a figure D that's situated on the bottom part of the right side of this slide. And this figure gives the spectral sensitivities of three photodiodes: silicium, gallium arsenide, both sensitive in the visible part of the spectrum, and a special diode for a large wavelength. Detailed information on device characteristics and performance of other types can be found in data books of the manufacturer. A PSD is a light-sensitive diode that is not only sensitive to the intensity of the incident light, but also to the position where the incoming light beam hits the diode socket, as you can see here. And this figure shows schematically the configuration of a lateral silicon PSD. The device consists of an elongated PN photodiode with two connections at its extremities and one common connection as a substrate. An incident light beam can penetrate through the top layer down to the depleted region around the PN junction, where it generates electron-hole pairs. As in a normal photodiode, the junction is a reverse bias. Due to the electric field across the junction, the electrons are driven to the positive side, and the holes move to the negative side of the junction. I agree with you. So the electrons arriving in the N region flow through the common contact to ground, and the holes in the P layer split up between the two upper contacts, producing two external photocurrents, I sub A and I sub B. And figure B shows an electric model of the PSG. It is used to explain how the current division depends on the position of the light. The photocurrent, modeled as a current source I photon, this side, originates from the points where the beam hits the diode. The division over the two contains contacts is determined by the resistances from these points onto the two endpoints RA and RB. Applying Kirchhoff's current law yields for the two output currents. Let's see this first block. Assuming a homogeneous resistance over the whole length of a PSD can be rewritten as you can see on the second. And generally, the origin of the coordinate system of the PSD is chosen in its center. And thus, X is the position of the light beam relative to the center where X equals 0, right? And further, when the total length of the PSD is equal L, as you can see on this part, the distance in the figure A equals L over half L plus X, and B equals L minus A. So let's see here the third block. Apparently, the difference between the two output currents, AI sub A minus A sub B, equals minus 2xi over the L, and is linearly dependent of X and I photon. However, it is preferred to have an output signal that only depends on the position of X and not on the light intensity of the incident beam. In order to obtain such an output, I sub A minus I sub B is divided by the full sum of these values, as you can see here on the this part of it. It gave us Si photons and resulting, let's see, as these photon equations as a whole. So, to perform an intensity-independent position measurement, the PSD should be connected to an electronic interface for three signal operations: addition, subtraction, and division. A PSD is essentially an analog device. The photocurrents vary analogously with the position of the incident light beam. And this is one of the reasons why researchers have designed PSDs with on-chip or analog signal processing to accomplish intensity-independent output signals according to our last equation. With the PSD in the figure A on the left side, the position of the light beam can be determined only in one direction. For a 2D measurement, a 2D PSD is required. And this type of PSD has a square-shaped sensitive surface and two pairs of current contacts, one pair for each direction. Its operating principle is exactly the same as for the 1D PSD. The linearity of a PSD depends largely on the homogeneity of the resistance in the top layer. In the central part, it's about 70% of the total length of area. The linearity is better than 1%, whereas the edges, the linearity error rises significantly. And this should be considered when operating the device in that area. The range of a linear PSD is almost equal to its length, from several millimeters up to 10 centimeters. The width is a few millimeters. A two-dimensional PSD measures 1 to 1 and up to 4 to 4 times 4 centimeters. The total resistance between two opposing contacts is several kilo ohms. Devices with larger size are difficult to realize in silicon. Other materials are being investigated to increase the lateral dimension. For instance, PSDs made from hydrogenated amorphous silicon, ACH, and have been realized with a range of 10 times 10 centimeters and comparable sensitivity. Research is going on to further improve the detectability of PSDs and to reduce the effect of the ground line. Most PSDs are made of silicon, hence their spectral sensitivity is comparable with the normal silicon photodiode. Most LEDs and laser tiles match well in this respect with the PSD. A PSD responds to the optical center of intensity of the incident light. Non-homogeneous background light causes a shift of these points, resulting in a measurement error. And you should note that homogeneous background light changes the scale factor of the system, as can be seen from this last equation here on the bottom of this slide, where an equal contribution to the current cancels in the numerator, but add in the denominator. A more in-depth analysis of the effect of environmental illumination sources for a two-dimensional PSD. In general, there is just one light spot from the laser, of which the position can be detected. In case of multiple light spots, the beams can be distinguished using modulated light on different pairs. The PSD can be used for contact-free displacement measurement. And now let's start another topic, subtopics of today's lecture. It's called optical displacement sensor. A simple, though rather inaccurate method to measure displacement is based on the inverse quadratic law. The light intensity from a point source decreases with the square of the distance. We distinguish two possible modes, the direct and the indirect mode. And figure A and B on the top part of this slide shows a general setup according to the direct mode. In the direct mode, the transmitter, it means LED or laser tire, is mounted on a fixed part of the construction, while the sensor is positioned on the moving part or target, or maybe a vice versa. Comparing figure A and B makes clear that the light intensity in watts per square meter drops with the square of the distance. Assuming a homogeneous light beam over the complete beam angle in the configuration over A, in figure A, the sensor output I is inversely proportional to the square of the distance. So let's see equation on the slide here. Actually, the inverse square law is just an approximation, since the emission is not homogeneous over the whole cone, as can be seen on the directivity diagram on a figure G. Evidently, the sensor output not only depends on distance, but also on the source intensity and the sensitivity of the sensor. These parameters should have sufficient stability to be able to distinguish their changes from displacement-induced intensity changes. The stability requirement can be weakened by applying a second sensor with fixed position relative to the source as a reference. The output quantity is the difference, or better but more complicated to implement, the ratio of both sensor signals. If both sensors have stable, identical sensitivity, source instability can be completely eliminated, and the final accuracy is limited by changes in the difference of sensor parameters. And figure C shows the indirect mode suitable for contact-free distance measurement. Source and sensor are mounted both on a fixed part of the construction, and the source casts a light beam on the target, which scatters the light in all directions, as you can see in this one. Diffuse reflection you must see here. And we disregard here specular reflection for simplicity. Most surfaces behave as a Lambertian surface. In other words, they scatter the incident light in all directions equally. Actually, the object acts as a secondary light source. In the same way, we see the moon by the sunlight scattered from its surface. The intensity of the detected light depends on the distance from the emitter-receiver system to the reflecting target, and hence is a measure for the position of a moving part. The intense square law also applies for this configuration, as long as the target intercepts the full beam. If, on the other hand, the target is small, as shown in the figure D, the reflecting surface area is constant, that of the target. The irradiance incident power per unit area of the target decreases with the square of the distance from the source, because the surface area is constant. The illuminated target acts as a secondary light source, the light of which is measured by the sensor. For this part, the inverse square law also applies. So in total, the sensor output drops with the force power of the distance between source and target, as you can see at this one. And note that the output depends also on the angle of the object surface relativity to the optical axis of the source. And the force power dependence results in an even smaller measurement range. And clearly, the design of a proximity sensor must be such that the object always intersects the whole beam. In other words, a narrow beam is a perfect, like last the seconds approximation, since it does not account for the directivity of the source and the sense or an inhomogeneous light beam. But nevertheless, they are useful for a quick check during the design process. For contact-free distance measurements, according to figure C and D, special devices are available in which the emitter and receiver are mounted in a single housing, as you can see in this slide. When configured for a small distances, this sensor system is referred to as an optical proximity sensor. The optical axis make a fixed angle, as can be seen on the figure A on the left part of the slide. And light can only travel from transmitter to receiver when the reflecting target falls in the area where the directivity curve of the transmitter and receiver overlap. As you may see, all parts overlap. The useful range of the sensing system is somewhat smaller. Both the lower and the higher limits of the direction range are set by the configuration geometry and by the directivity characteristics of the device. So X should be between XA and XB. All considerations given for this type of linear displacement sensors call for angular sensors too. Angular sensitivity is obtained using the direction sensitivity of the source or sensor. The contact-free distance sensors discussed here are simple and cheap, principally due to the analog nature with the reflection measured a very high resolution down to 0.01 micrometer and can be obtained. However, the accuracy is low because since the output is an intensity signal, intensity variation due to the other causes will taken as a displacement. For instance, changes in the target reflectivity, the intensity of the emitter, and the sensitivity of the receiver all contribute to a change in the output signal. The effect of different reflection coefficients is depicted in this right figure, figure B, where the upper curve refers to a surface with a relatively high reflectivity, and the lower dotted one to a more absorbing surface. Compensation, balancing, and feedback make the output more tolerant to changes in the path. Instead of a single receiver, a pair or a quad means 4 tiles arranged in a 2x2 matrix is used. The position of the incited light beam is controlled in such a way that all sensors have the same output. This guarantees a fixed position of the beam, exactly between the tire pair or in the center of the quad. Displacement information is derived from the actuators controlling the beam position. In this way, accurate position information is required with a rather inaccurate optical sensor. Similar concepts are used in CD players to keep the reading path exactly on the right track of the disc. In mechatronics and many other applications, it is not always of primary importance to find the exact distance. The detection of an occurrence would be sufficient in many cases. The open or closed, presence of person or object. For this purpose, special optical sensors have been constructed with a wide range of specifications. Systems in which the sensor faces the source or direct mode have the widest range up to 35 meters. Indirect mode systems have a smaller range because only part of the scattered light will return to the sensor. With special reflectors or retroreflectors, the maximum range is about 10 meters, when only the reflection of the object itself is viewed at a distant range in several meters. Up to the here-only sensor, its reflection mode have been discussed. Measuring linear and angular displacement can also be performed by an intensity method in transmission mode. A simple configuration is given in this figure. Light transmission is modulated by the tapered slot in the moving mass. A very cheap and simple linear displacement sensor suitable for applications with low demand on accuracy. A rotational version can be made in a simpler way with a tapered slot in a circular segment. The dimensions of the slot are chosen such that the whole displacement range is covered from 0% to 100% of transmission. The principle is also suitable for measuring very small movements, like a sub-millimeter. High sensitivity but small range is obtained by a configuration with a narrow slot in the moving mass and a fixed slot in front of the receiver, as you can see on a figure C. By shaping the slot in a particular way, an arbitrary transfer function can be obtained. For instance, a logarithmic or a parabolic relationship between displacement and transmission. For each application, optimal dimensions can easily be found by inspection of the amplitude of the movement by the monitor. A triangle is completely determined by some parameters, sizes or angles, a property that is used to find an unknown distance. Assume x is in this figure is an unknown distance. When one side A and the angles alpha and beta are known, the other sides x and y follow from the two formula you can see at the bottom here. And this principle is used to measure displacement or distances in a variety of situations. And this A figure shows a configuration using the direct mode. With one fixed distance d, as you can see as opposite, the fixed angle of alpha when you might choose your distance of the angle, or the PSD or the triad array, and the unknown distance can be calculated. In this configuration from one-dimensional displacement measurement source, the position x of the target has to be measured while moving along the x-axis here on the horizontal plane. It carries an omnidirectional light transmitter viewed by PSD or a line camera. The sensor is positioned in the focal point of the lens with focal distance f and this creates a sharp image on a PSD. Only if the spot is far away, which in most practical situations is indeed the case. And in general, the optical position and orientation of the PSD should fulfill the Scheinflag configuration or Scheinflag condition in order to have the spot always in the focus of the PSD, irrespective of the distance. From figure A, it follows that the measurement range travels from XA to XB from the left to right depends on the size of the PSD from YA to YB. And the focal length of F can be further be adjusted with the parameters G and alpha. And figure B gives a configuration in indirect mode. A light beam from a laser source has a spot on a suitable, well-defined point at the movable target. And you can see here, on this movable target, this moving to the horizontal plane, and part of the scattered light is projected onto the PSD. A displacement of the target causes a displacement of the projected light spot on the sensor. The X position of the laser source is irrelevant here, as long as the spot intensity is large enough to create a bright spot on the PSD. And clearly, each target position X corresponds to a spot position Y on the PSD. And this relation depends on the geometry and the focal distance of the lens, and can be found using the goniometric relation at this one for the tangent for alpha with y over f is a tangent beta, and a over x give us tangent gamma, and we arrive at y and x. And this figure shows the effect of the parameter alpha on the range and on the transfer characteristic. The horizontal line, it's a cotangent alpha, and tangent alpha represents the values for x equal 0 and x becomes to infinity, respectively, in this case for alpha equals 1.25. 1.25 radian. At a fixed length of PSD, the measurement range increases for increasing d and decreasing f. In general, the transfer is nonlinear. Only for alpha equals half pi, the optical axis of source and the sensor are perpendicular, and the transfer is linear. What it means? It means that y over f is a proportional the same as x over d, so the range is rather small. In case when alpha equals 0, parallel optical axis, the transfer is simply the inverse. It means that y over f, it will be negative sign for d over x. And in practice, a compromise must be made with respect to range and inaccuracy by nonlinearity. The range can be enlarged using rotational mirrors, a technique that will be discussed a bit later on application. The size of the light spot image on the sensor depends on the beam diameter and divergence, and may be substantially larger than the required resolution of the sensor. For a PSD, this is not very relevant because it responds to the optical center of intensity, which lies on the main axis of the light beam, right? And obviously, the spot size should not exceed the width of the PSD. A more serious problem is the low S/N ratio due to the poorly reflecting surface material, a slanting angle of incidence, or simply a too large distance. And using multi-sensor techniques and signal averaging, the accuracy can be improved over a factor of 10. When using a diode array, instead of a PSD, the light spot may simultaneously activate several adjacent elements of the array. And therefore, the element in the center of all activated elements for the medium should be selected as being the best position of the spot. While designing a displacement sensing system, often a trade-off has to be made between one-dimensional or two-dimensional PSD and a line or matrix camera. And this table presents some basic differences between these two devices, which could be helpful in making a proper choice. But you should be noted that numerical data are typical, and higher values for resolution and speed are available. The optical sensors described in these sections are digital in nature. They convert through an optical intermediate and the measurement quantity into a binary signal, representing a binary coded measurement value. Sensor types that belong to this category are optical encoders, designed for measuring linear and angular displacement, optical tachometer, measuring angular speed or the number of revolutions per unit of time, and optical barcode systems for identification purposes. Optical encoders are composed on a light source, a light sensor, and a coding device. It must much the same as a general setup on this stick. The coding device consists of a flat strip for linear displacement or disc for angular displacement, containing a pattern of alternating opaque and transparent segments, the transmission mode, or alternating reflective and absorbing segments in case of the reflective mode. Both cases are illustrated in this figure. The coding device can move relatively to the assembly of transmitter and receiver, causing the radial transfer between them, switch between a high and low value. In the transmission mode, the encoder consists either of a translucent material like glass, plastic, and mylar, covered with a pattern of an opaque material, for instance, a metallization, or just the rubber, for instance, a metal plate with slots or holes. Two basic encoder types are distinguished: absolute and incremental encoder. An absolute encoder gives instantaneous information about the absolute displacement or the angular position. And this figure gives examples of absolute encoder devices in transmission position. Each or discrete position corresponds to a unique code, which is obtained by an optical readout system that is basically a multiple version of figure A. The acquisition of absolute position with a resolution of n bits requires at least n optical tracks on the encoder and the same quantities and separate samples. Obviously, the maximum resolution of an absolute encoder is set by that of the least significant bit, LSB track. And evidently, it is the outer track of the angular encoder. Practical limitation of the resolution is limited by the dimension of the detector. Special integrated circuits, including photodiodes and built-in compensation, have been developed to maintain the performance also with high-resolution encoded disks. The nature of binary code is polystropic, which means that two or more code bits may change for a one-dimensional LSB displacement. See the linear encoder on a figure A on the upper track. Mechanical tolerances will introduce error codes between two adjacent binary forms. For this reason, most encoders use the gray code, which requires also the minimum number of tracks at a given resolution, but is monostropic. At each LSB displacement, only one bit will change at a time, as can be seen from the linear encoder in the lower track of figure A. Serious disadvantages of an absolute encoder are its limited resolution, the large number of output sensors, and the consequently high price. A much better resolution is achieved by the incremental encoder, of which this figure shows a typical example for linear displacement. It has only one track consisting of a large number of transparent slots. In the angular type, these slots are arranged radially along the circumference of the optical disc. Principally, the incremental encoder needs only one source and one sensor, facing each other through the chord disc or angular or the scale in linear. The output of the sensor changes alternatively from low to high when the encoder is displaced relatively to the source sensor system, generating a number of pulses equal to the number of light-dark light transitions, although the actual output signal does not contain information about the absolute position of the encoder. And this position can be nevertheless be found by counting the number of output transitions or pulses started from a certain reference position. The reference position is marked by an extra slot in the disc or scale. Once the position information is lost, for instance, due to a power interruption, the system should go to the nearest reference maker. At very large scales, this could take too much time, and therefore, long scales have multiple markers, which are coded to make them distinguishable from each other. And in this slide, the markers are identical, but positioned on different distances. The number of lines between two adjacent markers is a unique code for the marker position. If the incremental encoder is used in the same way as the absolute encoder, one sensor for each line, its resolution would not be much better, because the size of the sensor should not exceed the bits of one slot. However, the combination with a fixed mass position against the moving disc or scale gives a much higher resolution, as illustrated in this figure. The mass has an extension over several line widths and the same pitch as that of the scale. The light transfer changes periodically from a minimum to a maximum value and back for each displacement over the pitch of the optical pattern. If the scale and the mask are perfectly matched and aligned, the maximum light transfer is 50%, position x2 in this figure, whereas the minimum light transfer is 0 over the whole area of the mask, as you can see in position x1. So the sensor size is not limited anymore to the resolution. However, due to the mechanical tolerances and not perfectly collimated light, the minimum transfer is not completely zero, and these effects become more significant at decreasing light speed. In the ideal case, the sensor output changes linearly with the displacement or rotation over half a grating period. At continuous displacement, the output changes periodically as indicated with the triangular characteristic on this figure. One period of this triangle corresponds to a displacement over one grating period we measured as a P, a grating period we may see here. Unfortunately, real encoders show some deviations from the ideal behavior. For instance, the baseline of a triangle I in figure A on the bias here. A can be shifted upward, or the sync amplitude decreases due to the misalignment of the scale and the mask, resulting in a position that you can see in figure B. Adding a second moving grating and sensor offers some improvement. When the gratings are positioned, it means N plus half from P apart, the outputs I sub A and I sub B are in identified, as you can see from figure B and C. The difference between both outputs is a triangular signal that has a more stable relation with displacement, as you can see on figure D. The common offset is eliminated, and zero crossing define dark light transitions in a more reproducible manner. The incremental encoders discussed so far do not provide information about the direction of a displacement or rotation. They are useful for unidirectional displacement and as absolute velocity sensors, but fail when position information is required after displacement in an arbitrary direction. And this figure clarifies how to solve this problem. Two pairs of masks are now positioned at a distance roughly n plus 1/4 of the pitch. A displacement results in two triangular signals according to figure D. It means half pi radii out of the phase, as in figure A and B. And these triangular signals are converted to two binary signals, D1 and D2, having also a phase difference half pi, as you can see on a figure C. Such a conversion can easily be implemented using comparators that switch their output just on the zero crossing of the triangular signal. From these two signals, D1 and D2, the direction of the movement and can simply be deduced. A movement in the positive x direction results in the binary word sequence D1, D2 of 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, etc. So code fun 1 is followed by fun 0. And when the direction of the movement is reversed, code fun 1 is followed by 0, 1. By driving a pair of flip-flops, information about the direction is easily achieved, right? So The resolution of an incremental encoder can further be increased as follows. When the relation between displacement and output is known, this information can be used to find intermediate positions between the maximum and minimum values of the triangle. And hence, the incremental encoder offers the possibility to interpolate between successive slots, increasing substantially the resolution of the sample. And in practice, the output versus displacement is not a nice triangle as given in this figure, because the tops may be rounded or the shape is more trapezium-like. Better interpolation accuracy is obtained when the output is first converted into a sinusoidal shape. And this results in one or even two pairs of signals in quadrature. It means half-pi phase differences, from which the electrical angle can be reconstructed compared to the resolved signal processing in inductive and magnetic samples. Another way is the arctangent method. The quotient of two quadrature signals is a tangential function. So by taking the arctangent of this function, the displacement is obtained. And obviously, errors in the amplitude, offset, and phase of these signals introduce position error. Note that the measurement head of commercial incremental encoder may contain 4 masks to obtain direction sensitivity. According to this figure, zero crossing accuracy, as in previous figure, and interpolation all in one. This mask serves for detection for the reference markers. So the intrinsic resolution of an incremental encoder is set by the number of slots per unit distance or rotation. Apart from interpolation, the resolution can further be increased by employing the Vernier effect of the Moore effect. Two identical scales with patterns having a slightly different pitch cause, when superimposed alternatively light and dark zones along the encoder scale with a synthetic period L, as you can see on a figure A. Similarly, two scales with the same pitch but making a small angle cause also white and dark zones on a figure B. When the scales shift a distance of one pitch relative to each other, the dark zone shifts over a complete synthetic period. The Vernier period equals L, it's a pi 1 times pi 2 over pi 1 minus pi 2. And the configuration behaves as an optical displacement amplifier. Its amplification factor is inversely proportional to the pitch difference and can be very large for the pitches having slightly different values. The zones have an extension that allows the use of normally sized sensors. Direction sensitivity is obtained in the same way as illustrated in this figure, using two sets of source sensor sets. And here too, the system allows interpolation between two adjacent positions with maximum and minimum output, similar to the normal encoder. A special design based on this concept where both shifted and rotated masks are applied. The Vernier concept can also be applied in absolute encoders to enhance their intrinsically lower resolution. Details are dealing with an absolute angular encoder used to control a servo with two disks comprising only 3 binary tracks each. a resolution of 1.6 degrees can be achieved instead of 45 degrees with a conventional 3-bit code degree. The main errors of optical encoders are the quantization error. It's only about half n, where n is the number of binary tracks in an absolute encoder, or the number of lines in the incremental encoder without interpolation. And in this case, the max tolerances, the misalignment, and the eccentricity of the code patterns. And this table shows ultimate specifications of several encoder types. So far, we have considered encoders with linear regular code patterns and static light beams. Many other code patterns have been proposed to reduce instrument complexity, increase accuracy, or enhance applicability. Instead of a collimated light beam to fully cover and coded area, a scanning light beam as used for reading barcode is a useful alternative. And this approach allows the use of just a single detector and makes additional detectors for determining the direction of movement unnecessary. It is also easy to read codes with a non-regular format, for instance, pseudo-random code. Such codes may yield higher accuracy because they are less noise sensitive, and the scanning may slow down the system. But for many applications, such as navigation, this is not a serious limitation. Okay. Next lecture, we will be continuing studying optical sensors. And I hope now you enjoyed this lecture, and I'm looking forward to see you next time. Bye. Good luck.